Stanford University.
Good afternoon. Welcome to EE380. We're approaching Thanksgiving and the end of the quarter. Not to get all, we had to walk uphill both ways through the snow on you, but some folks in this room have maintained a host.txt file. That's relevant because it wasn't that long ago that the network was something small and could be understood and passed around by people through email or even postal mail or over the phone. Today's the number of computers is, in some sense, on the network, is in some sense unknowable because they pop in and off. But it's certainly very, very large. This mostly works because the world is fairly decoupled. And many of the big problems in naming and services are at the organization level. And surely an organization can keep track of its computers without much trouble. Except that there are now organizations that have hundreds of thousands of named and networked computing entities. And I changed terminology there because the world, virtual servers doesn't capture the awkwardness that we now have. It used to be that the network, we'd say the network was the computer. Well, the network is now in the computer in many senses. Not only is it turtles all the way down, but it's turtles all the way in. This brings us to today's talk. We know how to manage clusters of thousands, tens of thousands of machines, but we're seeing data centers that are in some sense, or in many senses, 10 to 100 times as large. And we can't manage them as independent fiefdoms. They're monolithic entities and their complexity is growing very, very fast, as is our dependence on them. And in fact, data centers actually too small. Google, from my point of view as an outside person, is not a collection of 40 data centers or 400 data centers or 30 data centers. I don't care what the number is. It's one. And they have to preserve this illusion for me or I go to Bing. So without further homilies, Amin Vahdat, from UC San Diego.
Thank you very much. Thank you very much. I'm very excited to be here today, and I will be telling you about our work in data center networks. I'll start off with just a brief commercial. This work is part of the UCSD's Center for Network Systems. We're fortunate to have support from our industrial partners, currently Cisco, Qualcomm, Google, Sun, HP, Network Appliance, and Motorola that work together with about 20 faculty members in the center and on various research projects. This is one of those research projects, and I think it's fair to say we wouldn't have been able to carry out this work without significant input from industry, as I'll talk about in a second. I also want to make it clear that I'm just the mouthpiece for a bunch of very talented students and staff at UC San Diego. I was actually shocked when I put together this slide because I hadn't realized just how big the group had gotten. Some days it's a bit overwhelming having to talk to all these fine folks who have a bunch of very, very interesting ideas. In terms of acknowledgements, it is multidisciplinary. As I mentioned, we've had significant support from industry, in particular on the ideas and requirements side. So this work has been informed by discussions with HP, who's also been generous in supporting the work monetarily, Ericsson, Cisco, Facebook, Yahoo, Google, and Broadcom. And without sort of the back and forth with people in industry, we wouldn't have known what problems we should be solving. We've had significant support from the government. The National Science Foundation has given us a grant to build out I put data center network in quotes on this slide because it's a 300-node prototype, which is substantial for a university. But of course, we're talking about 100,000 node data centers out in places like Google and Microsoft, Yahoo, etc. So one question and one interesting challenge for us is how do we demonstrate our ideas when we claim we can go to 100,000, a million, these big numbers, and we're limited to interesting scales in a university, but certainly not the scales that people are building on a somewhat regular basis today. And we've actually, it's gratifying to be here at Stanford because this work, frankly, wouldn't have been as easy to do if it weren't for some technology that came out of here. In particular, the NetFPGA and the OpenFlow projects were the basic building blocks that we leveraged to start this work. And of course, we're now moving beyond to commercial switches, larger scale prototypes, etc. But we wouldn't have been able to get started nearly as quickly if it weren't for some of the great work that came out of here. Okay, so motivation. Data centers are everywhere. So in my mind, the increasing and perhaps vast majority of computing, storage, and communication in the internet 10 years from now is going to be taking place in a relatively small number of dense data centers. So virtually all of the Fortune 500 companies have these large data centers, data warehouses. Here's Walmart's data center. Here's the blueprints for a 200,000 square foot data center that recently went up in Oregon. Here's a map as of a couple of years ago of the 36 worldwide data centers that Google had. Google's on record of having at least 1 million computers across their data centers with more than 10 million cores. So tremendous scale, lots of storage, lots of computing, and lots of network requirements within these data centers. So for our work in particular, over the past decade plus, there has been tremendous commoditization in the data center. So inexpensive commodity PCs and storage devices are the basic for computing and storage. Right? So the same machines that you and I might buy from Dell or the equivalent are more or less what's going into these data centers. Same for the disks. However, the network is still highly specialized. Right? We know how to incrementally build more and more computing power. Right? If I have a factor of 2 more users and I need a factor of 2 more computation, okay, go buy factor 2 more servers. But same with storage. But on the network side, it's not straightforward to figure out how to build out a network that can deliver the necessary communication bandwidth among all these hosts. Okay, the network is still highly specialized. Furthermore, the data center is not a small internet. The assumptions that might go into a good internet wide area network infrastructure don't match up to the requirements of the data center. We are in one administrative domain. It's typically not adversarial. There aren't things like BGP, policy routing, et cetera, et cetera. And increasingly, though, bandwidth is the bottleneck. And we have many applications that are performing all-to-all computing in many cases. Cloud computing, of course, we're hearing a lot about in the press. Let's take one example, Facebook. Right? So every request that you make on Facebook to access your front page might involve communication with 1,000 computers. Right? So you make a small HTTP request in, and that front-end HTTP server has to go gather the contents of your page from 1,000 different compute elements on the back end. And of course, they have a very limited amount of time, a few hundred milliseconds, to get all this information. So it's highly bandwidth intensive. Search, of course, we're probably all familiar with. Every search request you make to Google or Bing requires communication among 1,000 plus computers. Even Amazon, you go to Amazon.com's front page. If you've noticed the density of information on that page, that information is not stored on just one computer. Just getting the index.html for the front page, don't worry about buying something. Hundreds of computers are involved, again, in a small number of milliseconds to gather all that information and return it to you. So you make a small request, you get a relatively small reply, but the synchronization or communication that's required on the back end to service that request is rather large. Data analysis is an increasingly important problem across many different companies, a lot of startups in this space. So we have the online side, Facebook, Amazon, Microsoft, Google, et cetera. But on the back end, when Amazon wants to figure out exactly what to put on your front page because they want to make the most money possible for every time you visit their page, they basically analyze every visit that you've ever made to the site and maybe join it across every visit that anybody's ever made to their site. That requires, of course, lots of storage, but it's effectively one very big database join operation. And this data of every visit to Amazon ever is, of course, stored across thousands, tens of thousands of computers. And when you're doing a join across data spread across thousands of computers, it's a very bandwidth-intensive operation. Okay? So we're living in this world where lots of communication, perhaps the vast majority of the communication in the internet, is going to be taking place in these data centers. Worse, we have all-to-all random communication taking place in these data centers. Right? Highly unpredictable, random, and lots of bandwidth in aggregate required from one point in the data center to another. So in the data center, there are a number of important network design goals. We'd like to, as I was motivating earlier, have scalable interconnection bandwidth. What I'd argue for is full bisection bandwidth between all pairs of hosts. Okay, put another way, the aggregate bandwidth in your data center should be equal to the number of hosts times the host's NIC capacity. Okay. So let's put some numbers around this. Let's say I have a 100,000 host data center, not an unreasonable number today. Let's say I have 10 gigabit NICs on each host, which of course you can buy, but pretty soon are just going to be becoming standard on motherboards. So at that point, 10 gigabits per second, 100,000 hosts, we're talking about a petabit per second network that we have to build. And I'd like that to be the communication fabric for my data center, a petabit switch. We want to do this, build this petabit switch, while maintaining economies of scale. So the price per port for my network should be constant with the number of hosts. Right? There shouldn't be any nonlinearities as I go from 10 to 100 to 1,000 to 10,000 to 100,000 hosts. And this means that I have to leverage commodity parts. And in the networking world, this means I have to leverage commodity merchant silicon. I'll say a few more words about that later. There should be a single network fabric. In the enterprise, at least over the last 10 or 15 years, there's been a significant amount of fragmentation on networking technologies. I might have 2 or 3 separate networks to each host, maybe InfiniBand, maybe Ethernet, maybe fiber channel. Everything should be unified in one host. And management needs to be significantly simplified. Right? In a 100,000 node data center, I might have thousands, perhaps even 10,000 plus switching elements. And I might know how to manage my 100,000 node data center as if it were a single computer. Right? We have programming models that are emerging like MapReduce, like Dryad at Microsoft, that say, you know what, I want to run on 20,000 computers as if it were one large supercomputer. And that's done regularly at the large companies. But when I look at my network, it still looks like 10,000 switches. Whereas what I'd like is a 100,000 port petabit switch. And I'd like to manage it as such. Okay, so this all argues for scale-out networking. Right? We know how to do scale-out computing and storage. Right? I can have aggregate storage and computing growing linearly with the number of commodity processors and disks that I have in my data center. I need more processing, more disk. I go buy more elements from Dell or whoever. And it's a quote-unquote small matter of software to enable this functionality. But we've built the software. Right? We now know how to manage the disks and the processors as if it were one large computer. The alternative to scale out, of course, is scale up. And this had been the model previous to these large clusters that are driving the data centers. Whenever you ran out of computing power or storage capacity, you would go throw it out and buy a bigger computer or a bigger disk, right, with all the obvious disadvantages. But that's roughly where we are with the network today. So there's no technology that will enable scale-out networking. In my model for the network, you should be able to go plug in elements that give you more ports, that let you plug in more computers, and you should be able to plug in elements that give you more bandwidth. Okay? So you figure out how much bandwidth you need for your data center, how much you want to oversubscribe things. I've argued for no oversubscription. Everyone should be able to talk to everyone else at full speed, but maybe for your data center, for your communication needs, you're satisfied initially with a factor of 10 oversubscription. So go buy enough modules that you can just go plug into some rack that give you that much bandwidth. And if you outgrow that, maybe because you've added more ports or because you're running more communication-intensive applications, go plug in more modules that give you more bandwidth on the fabric side. Okay. That's what the switching infrastructure should look like. Okay, so with all that background in mind, let's consider briefly at least what the current data center network topologies might look like. Data centers are organized around racks. Right? Racks might have 40, 45 compute elements in them. At the top of a rack is a so-called top-of-rack switch that will provide full bandwidth among all hosts within that rack. Today in the data center, the big companies are making a transition, but still largely we're at 1 gigabit per second networks. And so I might have 40 hosts in a rack. I might have a top-of-rack switch that will allow all those hosts to talk to one another at 1 gigabit per second. These top-of-rack switches will have some number of 10 gigabit uplinks, say, to an end-of-row switch. So I organize my racks. Each rack has a top-of-rack switch, and each one of these top-of-rack switches will have uplinks to an end-of-row switch. This will be non-commodity parts. So let me step back. The top of rack switch is commodity. Right? You can go buy a 48-port switch at Fry's or your favorite vendor for a couple of $1,000s. And it's non-blocking, et cetera, et cetera, et cetera. Once you start moving to this end of row, where now you're talking about a 10 gigabit switch, maybe a 48, 96, perhaps 128 ports, it becomes a non-commodity piece, very expensive, and it's limited in terms of its size. The biggest non-blocking 10 gigabit Ethernet switch that you can buy today, at least last I checked, is 128 ports. Okay. And in the very big data centers beyond say 1,000 computers, you're going to have a third level in the hierarchy, a core switching hierarchy, that are going to interconnect the different end-of-row switches to one another. So oversubscription is common in these data centers. If you go to Cisco and ask them for their design guidelines, right, go to Cisco and say, please help me build a data center. For a couple of thousand computers, they might tell you to oversubscribe your network by factor 2.5 to 8. Right, what this means is that if I've got a gigabit link, I might only be able to get, say, 100 megabits per second, 125 megabits per second across my data center. In a recent paper from Microsoft describing some of their data centers, they say that their networks are oversubscribed in some cases by a factor of 250. Right? So I've got a gigabit link, and that means that to a remote computer in the same data center, I might get 4 megabits per second. Now, we just did some recent experiments on latest Intel processors. We had two 10 gig NICs in these processors. We were able to drive 20 gigabits per second between a pair of hosts with 20% CPU utilization. Okay. So now imagine a computer, and this is a commodity part, just again, ordered, in this case from HP, and you're up and running. 20 gigabits per second, 20% CPU utilization. Full commodity, and now imagine that I only get 4 megabits per second across my data center. It's tough to build a balanced system in the case. It's tough to program a system where I have such vast differences in bandwidth if I might get 10 gigabits per second here, 1 gigabit per second here, 100 megabits there, 4 megabits there. Worst part of this story is that it is difficult to scale this traditional topology to 10 gigabits per second because it relies on aggregation to higher speed non-commodity parts moving up the hierarchy. Right, so I have my commodity 1G switches at the top of my rack, but I'm going to non-commodity 10G switches up the hierarchy. Okay? So now if I decide that I need 10 gigabits at the edge, and I would argue that today we do, given the processing power that we have at the edge, how do I aggregate up? Right? There is no 40 gigabit, 100 gigabit Ethernet. 40 gigabit is now just becoming available, 100 gigabits a number of years out. When they do become widely available, they're still going to be much more expensive and limited in port density moving up this hierarchy. Okay, so the key challenges that we face in the data center today are performance, right, cost, how to do routing across this topology. I won't spend much time on this, but I'll briefly motivate it. The internet is about getting packets from one point to another, not about getting it there most efficiently. In the data center, you have significant multipath. You have to have multipath to get the aggregate bandwidth that you'd like. What that means is that there may be 100 or 1,000 different paths, all equally good between one host, between a pair of hosts. Internet protocols aren't good at picking among them. Energy. As we scale up the speed of the network, we are going to have an increasing fraction of data center energy committed to the networking infrastructure, and as it turns out, cabling is a big problem. Yeah?
You haven't mentioned latency as a key challenge for data center network.
Yeah, I think latency is a great point, though I would also say that for the kinds of SLAs that people are looking at today, in places like Facebook, Microsoft, et cetera, when they're living with 300 millisecond SLAs, the sort of extreme latency that, say, RAM Clouds is considering hasn't been a driver. Now, of course, you and I have talked offline, and I agree with you that latency moving forward is going to be critical for enabling us to program the data center as if it were one single computer, basically removing this potentially artificial illusion that things are vastly far away as you move across the data center. But I would say, so one, I should probably add latency to this slide, but two, the traditional, if you ask the data center operator at Microsoft, Google, et cetera, what's your top 5 problems? Latency probably wouldn't land on the list today. That's not to say that it shouldn't. Okay, so let's consider price. right? When we're building a large-scale network, we have to consider the price. And here is a brochure. This brochure is now a year and a half old, so the absolute numbers have changed, etc. But I'm just trying to make a point. This brochure shows for 4 different companies, and of course the brochure is made by the yellow company, the total solution price as a function of line rate gigabit Ethernet nodes in your data center. I apologize if this is sort of hard to see. 100, 256, 512, and 1,000 hosts. Right, 2 interesting things to take away from this brochure. One is a significant nonlinearity as you step from 512 to 1,000 hosts. Okay? And this nonlinearity comes from the fact that the biggest switch that company Yellow sells was 512 ports, still is 512 ports at the time. Once you go beyond that, you have problems. Right? And this is why I was saying the price per port should be constant. But there's a huge jump even for company Yellow, who made this brochure. And of course, it's earlier for the other companies because their biggest switch was smaller. That's one of the things that they wanted to tell you. But the other interesting thing was that company Yellow was essentially bragging about the fact that they would charge you $4 million for the switching infrastructure for a 1,000-node gigabit network. Basically, they wanted you to pay $4,000 per port to interconnect $1,500 PCs. So now it's not so surprising that you would oversubscribe your network by a factor of 10 or 100. It doesn't make sense for me to pay $4,000 a port for the PCs that are half or less that cost. Okay, so in some earlier work, we did a study considering basically how would you build data centers that might scale out to 20,000 ports. Seemed like a reasonable number for a year and a half, 2 years ago. And the blue line basically considered the best retail prices we could find for 128 port 10 gigabit switches. And what you can see is that the blue line, is 100% bandwidth, meaning that everybody can potentially talk to each other at full speed. Gigabit, okay, not 10 gigabits. So this shows that for our analysis, a bit more conservative than the earlier one, it would cost $27 million to interconnect 20,000 hosts at gigabit, or about $1,350 per port, if you were to go build the traditional data center topology that I showed you earlier. And this green line here shows you an alternative approach that I'm going to be telling you about briefly around commodity switches, identical commodity switches. Again, all we're doing is riding the commodity wave. Right? Rather than having to pay for the very expensive 10 gig switches, we'd go with commodity gigabit switches. And so you can get a factor 10 plus reduction in the cost, getting it down to that, say, $100 or $200 per port rather than $1,350 plus. Okay. So here's the idea. It's a very old one. Goes back at least 50, almost 60 years now. This is to basically get scalability in your data center network fabric using a variant of a class topology. And then Charles Claus developed this topology for telephone networks around the early 50s. Okay? So here's an instance of a class topology called a fat tree. It's a 16-port switch built from identical 4-port switch elements. Okay? So for simplicity, I have 16 hosts along the bottom, and they're interconnected by these 20 switches, all 4 ports each. So I've organized these 16 ports in my switch that I'm showing you here into pods. 4 pods in this case. I've highlighted one here. Each pod is a 2-array 2-tree. That means that it has 2 links going up at each level of the tree, and the height of the tree is 2. Key takeaway here is that you'll notice there's 4 hosts connected to the pod. And at the second level, with the X and the lines, we have 4 links. So if I'm careful about scheduling my links, I can have all these 4 hosts talking to one another at full speed, independent of their communication patterns. Now, there's a challenging scheduling problem there, but it's possible. If we consider the fat tree as a whole, I have 16 links at the middle level, 16 links across the top level. So once again, if I'm careful with my scheduling, I can allow everybody to talk to everybody else at full speed. Okay? So this is called a rearrangeably non-blocking topology. The entire fat tree is a 2-array 3-tree. The height is 3. There are 2 links going up at each level to the root. Okay? I also call this a multi-rooted tree. So this isn't a very interesting way to build a 16-port switch. You wouldn't ever build a 16-port switch this way. But the interesting part of this is the scaling properties. So I showed you how to build a 16-port switch from identical 4-port switching elements. But if we generalize to k-port switching elements, you can use 5k squared over 4 k-port switching elements to support non-blocking bandwidth among k cubed over 4 hosts. Okay. So now let's consider 48 port switches. And the 48 port merchant silicon chip that'll support gigabit Ethernet might cost $100. I can support 27,648 hosts non-blocking, right, just using this formula here, using 2,880 of these elements. By the end of this year, a number of different companies are going to be selling 64-port 10 gig switches. Right? Just entire switches on a chip, and they might cost somewhere on the order of $500 each. So you plug that in, and all of a sudden you get 65,000 hosts that you can support, potentially rangeably non-blocking at 10 gigabits per second, right, again with reasonable cost numbers. Right? So the nice thing here is that this approach does scale to 10 gig or 40 gig or 100 gig because it uses identical switching elements throughout the topology. We don't rely on aggregation to higher speed, non-commodity components moving up the hierarchy. Okay. And the other thing that we'll see here is that the regular structure of this topology simplifies the design of network protocols. So as I mentioned, the data center is not the internet. In the internet, you have to assume an arbitrary topology, obviously. Right? There's no control over the internet. Anybody can plug in anything anywhere. In the data center, you have some control over the topology. And as it turns out, these trees, whether you like this multi-rooted class tree or the picture I showed you earlier, has hierarchy built in. It's a multi-rooted tree, whether you go with the Cisco proposal, if you look at Facebook's data center network, Yahoo's data center network, Microsoft's data center network, Google's data center network, they all look like this. They might not be exactly organized like this, but they're hierarchically organized. So one of the key questions that we ask is, how do you make life a lot better, a lot simpler, a lot more scalable, a lot more efficient, if you can assume that you've got a multi-rooted tree underneath you? Now, you can't assume that no one's going to do a miswiring, so we have to be able to deal with that. But what if we could assume that you meant, at least, to build a multi-rooted tree, even if you didn't succeed?
Partial credit.
Right, exactly. And we're going to do the best that we can, given what you've built. OK, so why hasn't this been done before, given that this is an old 50-something-year-old idea? It has to be backward compatible with IP and Ethernet. So as I mentioned, if you look back at this topology here, in order for me to get this rearrangeably non-blocking property, I have to be careful about scheduling my multiple paths between sources and destinations. Default IP forwarding and routing would pick a single path between each source and destination, and oftentimes these paths will collide, giving you terrible bandwidth. And the bandwidth that you get becomes more terrible as you scale k. Okay? So as you make the network bigger and bigger, if you're not careful about scheduling a network, you're just going to do worse and worse and worse. Okay? So existing routing and forwarding protocols do not work for the fat tree. You have scalability challenges with millions of endpoints, especially in the face of virtualization. I talked about the management problem earlier. And you have this cabling explosion at each level of the fat tree. The downside to not aggregating to higher speed links is that you have 10 times more cables, potentially. Right? So if you're not careful, and some people have tried to wire up in a straightforward manner a fat tree, you might have your data center wind up looking like this. Okay. So right. A number of challenges that come up here. Our work is addressing a number of these different challenges. One is the basic switch architecture that I told you about, and that was presented in an earlier SICOM 2008 paper. We've looked at the cabling issues that come up here, and that was in a Hot Interconnects paper this year. Today I'm going to be telling you about the protocols that underlie this, supporting basically a single large layer 2 network fabric. Okay. We're also doing work on the routing and forwarding side. We're considering an optical interconnect to supplement our topologies. That's ongoing work that I'd be happy to talk to anybody afterwards. Okay, so our work on PortLand considers one aspect of this data center problem. How do you treat your, say, 100,000 port data center network as if it were one big switch, right, and manage it as such? So we want to have a single layer 2 fabric to 100,000 port, and I'll talk about some of the issues with layer 2 versus layer 3. supporting, say, 1 million end hosts in the face of virtualization. Say 10 virtual machines, each with their own IP address running on each of these machines. Virtual machine migration should be straightforward, so I should be able to move any virtual machine from any host to any other host dynamically without disrupting any of the communication that might be going on to that machine, any of the IP state that might be cached throughout the network. We want to have zero configuration at deployment, or move in that direction. So we don't want to worry about assigning different subnets to every switch. We don't want to have to configure DHCP servers with our subnet masks, assign IP addresses, et cetera, et cetera, et cetera. We don't want to keep track of wiring information. We want people to be able to plug in switches and for the network to learn how to do forwarding, how to do routing, how to take advantage of the additional bandwidth that became available from plugging in this new module. Of course, there should be no forwarding loops. There should be rapid and efficient failure detection, native support for multicast, and first-class support for multipath routing and forwarding. Yeah.
At a network of this size, do you have problems with broadcast packets just consuming too much time on too many machines?
Yeah, I think that's an excellent question, and there are a couple of answers. One is, yes, of course, if everybody's doing repeated broadcasts to everyone, you're going to have a problem. So you might have to do some squelching. But it turns out that at 10 gigabits per second, right, if every host is doing a few broadcasts a second, it's going to wind up being a tiny fraction of your overall network bandwidth. Right? So I'll get into that a little bit more, but I think it depends on your deployment environment. One answer is we get rid of ARP and we get rid of DHCP. So what broadcast do you have left? And now you'll have some answers for me, and then our response would be those should be replaced with multicast groups. Okay, this is a complicated table. I'm not going to go through it. I'll just highlight a couple of interesting things. One is that people have tried to build large layer 2 fabrics over the years. One industry standard effort is Trill. A recent research effort is called Seattle. And I put PortLand, our work here as well. The interesting thing to take away is that there are some scalability and sort of backward compatibility issues with the previous approaches. So for instance, the amount of switch state that Trill has to maintain is order of the number of global hosts in the system. Right? So in Trill, every switch has to keep track of potentially 1 million endpoints. Same with Seattle. And the key thing here is this second column, the topology. Both Trill and Seattle assume a general topology. They assume that all the switches can be arbitrarily interconnected with one another. And in certain environments, you have to make that assumption. In PortLand, we assume that you meant to build a multi-rooted tree, that there's hierarchy built in. And what that means is that, for instance, we can have maintained switch in each, state within each switch that's order the number of ports in each switch. So tiny compared to the order number of global hosts. Our addresses are hierarchical relative to Trill and Seattle, which are flat, basically arbitrary encoding. The list goes on, but I think the takeaway is that yes, previous work has been done in this space, and we weren't necessarily, and actually absolutely, not any smarter than all the fine folks who've done work in this space. We just made the problem easier by assuming that we were living in this world with multi-rooted trees.
By the way, if you meant a small enough number of errors, or?
So in our work, you can have arbitrary number of errors. Of course, you might not have connectivity, right? But we're going to ignore all the links that violate the multi-rooted tree assumption. Okay, so here is the design overview for PortLand. Essentially, what we do is, again, use another old idea. We're going to separate node location from node identifiers. So I recently heard a very interesting talk from Vince Cerf, where he said the single biggest mistake, in retrospect, that he made in designing TCP and IP is to combine the host identifier with host location in an IP address. And at the time, of course, this was brilliant, because you weren't going to move these half-room-sized computers from one place in the network to another place in the network very often.
Unless it's an aircraft carrier.
Right. But still, it was a very reasonable optimization to make. But in today's internet, this causes some problems. So what we want to do is basically say, okay, IP address, that's your globally unique host identifier. You can have it forever. Your identifier is going to be your location, what we're going to do forwarding on, is going to be something separate. And for backward compatibility, what we're going to do is we're going to use your layer 2 MAC address as your location. And we're going to do this transparently to the end hosts. So the end hosts believe they have this flat 48-bit MAC address that was stamped on their NIC at the time of manufacture. We let them believe that. But internally within the network, we're going to do some rewriting to encode hierarchy. Okay. So the design of PortLand that's published leverages a fabric manager. Basically, you can think of it as a centralized, though of course potentially replicated, directory service that is going to maintain a mapping between IP addresses and the pseudo-MAC or PMAC node location identifiers that we introduce. So every host is going to have its actual MAC address, and we're going to introduce a pseudo-MAC address on top of it. And this pseudo-MAC is going to be sufficient to perform positional forwarding within my topology. And we introduce a LDP protocol that's the equivalent, say, of OSPF or ISIS routing. But rather than doing broadcast, we're going to do pairwise exchanges between switches for every switch to learn its location in the more general topology. Okay, so let's consider why, right, I've been taking it as given that we want to have a layer 2 fabric. So if you build a big data center network, you traditionally have two choices: build it as one layer 2 fabric or try to do layer 3 with IP addresses. So the big benefit of a layer 2 network is that it is plug and play. Right? It's going to run some spanning tree protocol or more efficient version of a spanning tree protocol, but you plug in a switch and everybody self-organizes and figures out exactly where they are in the topology. But the layer 2 network is going to have scalability challenges. It's going to do things like ARP. It's going to have to maintain state order of the number of hosts in the network. It's not going to have small switch state. But because any host connected to any port can have any IP address, it's one big subnet, it supports seamless VM migration. Okay, so that's an advantage. So again, stepping back for just a second, if I want to move a virtual machine from one switch to another, at layer 3, I would have to change its IP address because that switch has its own subnet number. And every host connected to that switch has to have the same prefix. This will break all kinds of state in my network. Right? So now, contrasting it with layer 3, it's not plug and play because I have to go configure my switch with a subnet number, tell my DHCP servers, et cetera, et cetera, et cetera. Scalability is better than layer 2, though there are some challenges there. It will have small switch state because I now have hierarchical addresses for forwarding, and that means that I can have small tables. But of course, now I have the problem with seamless VM migration. So, and again, I won't go through the particulars in any detail here. Bottom line is that the location-based addresses, as an IP with these hierarchical encodings, mandate manual configuration. I have to go tell the network what the hierarchy looks like. So let's quickly consider this question of cost within my switches. Right, one question you might have is 100,000 hosts, 1 million hosts. How much state is that really? That's a few megabytes. A few megabytes are cheap. We live in this world where we think gigabytes, right? I can put 100 gigabytes of memory in my end host. So why am I worried about having state in my switches for 100,000 or 1 million hosts? Well, so these commodity switches today have maybe less than a megabyte of low latency, power hungry, expensive on-chip memory. Right? So while we're used to living with gigabytes of DRAM, if you think about how much L2 cache an Intel chip has, 12 megabytes, right? And that's the L2 cache, not necessarily the even faster TCAMs, et cetera, that you might have to have for the on-chip memory. Furthermore, the commodity switches are going to be a generation or two behind Intel in terms of miniaturization. So with, say, half a megabyte of on-chip memory, I can only store about 32,000 to 64,000 hosts on chip. Right? So, but if I have 10 million, 1 million virtual endpoints in 500,000 servers in my data center, I'm going to be in a bit of trouble if I'm using flat addresses, right? Because I'd need, say, 100 megabytes of on-chip memory, even beyond what Intel can deliver on their chips, in order to be able to support all the state necessary to do forwarding for 10 million endpoints. Whereas if I have location-based addresses, I can use hierarchy. I might only need 100 or 1,000 addresses per switch for only about 10 kilobytes of memory. That's easily accommodated in these commodity switches today. Okay, so basically what we want to do in PortLand is maintain the plug and play of layer 2, introduce small switch state, right, and improve the scalability. So if we have a topology, a multi-rooted topology that looks like the above, we want to impose hierarchical addressing on the end hosts as learned by the network. So let me show you how that works. Right, so the scalability challenges that we want to address are address resolution. We don't want broadcast-based ARP. Routing. We don't want broadcast-based OSPF or ISIS. And forwarding. Right, we don't want to have large switch state. So let's layer hierarchy on a generalized multi-rooted tree. We're going to organize things into pods, as I was mentioning earlier. So pod, basically think of it as a layer of hierarchy. So we're going to have, in this picture, pod 0, 1, 2, and 3. And within each pod, each switch that's connected to end host is going to have a position. In the simple topology, 0, 1. Right? Might go up for larger topologies. So a PMAC, a pseudo MAC address, is going to consist of a pod number, position number, a port that's locally known on each switch, and virtual machine ID. That's again locally known on each switch. So basically the job of at least these edge switches is to assign a PMAC to every end host that's connected to them. Okay, so this is the key. And in order to do so, the last two bits here, the port and the VM ID, it can just do locally. What it has to do, though, is negotiate with all the other switches a unique pod number and the same pod number as the other switches in the same pod and a unique position number. So we want to learn this in a scalable manner that doesn't involve broadcast. Okay, so we're going to do this through a location discovery protocol. It's a new protocol that these switches are going to run. Right? At boot up, they're going to exchange LDMs, location discovery messages, on all their ports. So basically what we want to learn is their tree level. So going back to this picture over here, am I an edge switch? Am I an aggregation switch? Or am I a core switch? Right, corresponding to 3 typical levels. So it could generalize up, but basically what level am I in this multi-rooted topology? What's my pod number? Right? Aggregation and edge switches should agree on the same pod number for all the switches in the same pod. And what's my position number? So here is the basic operation. The key bootstrapping mechanism we're going to use is that edge switches are not going to hear LDMs from end hosts. So when they boot up, they're going to get location discovery messages on some of their ports, but not on others. Because end hosts, they see these the broadcast location discovery messages, and they say, okay, I need to ignore those. I have no idea what those are. And the end hosts aren't going to generate the location discovery messages. So after some number of rounds, what's going to happen is that the edge switch is going to say, okay, I have a bootstrapping mechanism. I've sent LDMs to my hosts up. Oops, excuse me. Some other switches have sent me LDMs, but I haven't seen any LDMs, in this case, say, from these bottom 2 hosts. So I must be an edge switch. So locally, a switch is going to know its identifier. The identifier can be the lowest MAC address for all its ports. It didn't know its pod number to begin with. It didn't know its position to begin with. It's now learned its tree level, 0 in this case. It's an edge switch. Aggregation switches, now we have the key bootstrapping mechanism. Aggregation switches are going to now receive some LDMs that identify the switches, some number of switches, as edge switches, and others as not knowing what their levels are. An aggregation switch, by definition, is one that's 2 hops away from a host. And now we can use this bootstrapping mechanism to take us one level further and have some aggregation switches learn their position. And now the core switches, the top of the hierarchy, is easy. Basically, you're going to get messages on all your ports saying, hey, I'm an aggregation switch. So moving up the hierarchy, we're going to be able to assign levels. Now, this is the first version of our protocol that I'm describing to you. There are a lot of corner cases to consider here, a lot of failure scenarios to consider here. And so we actually have an enhanced version of the protocol that we've implemented and we're working on writing up right now that is actually more decentralized, more scalable, and more robust to failures. Okay. So now once I've learned my level, what I'm going to do is I'm going to work with the other switches in the same pod to propose a unique position number. So in this case, I'm going to propose my position number as being 1. This other edge switch happens to propose a 0. What happens here is that I'm going to use the aggregation switches in the same pod to disambiguate and make sure that nobody proposes the same pod number. If they happen to propose the same position number, if they happen to propose the same position number, then they would basically the aggregation switches would come back and say, no, you can't have that. Try again. Pick a different random number, essentially. Okay. In this case, I hear yes back for both my proposals, so I know my position number. And now we're going to leverage our centralized directory service, the Fabric Manager, to get a unique pod number. Basically, we're going to have a edge switch propose a pod number, and the Fabric Manager will disambiguate between it and others in assigning a unique pod number to it. This case, 0. So now the edge switches have all the information that they need. They know their pod number, they know their position, they of course know their ports and VM IDs, etc., to assign pseudomax to all the hosts that are directly connected to them. So the Fabric Manager is going to play a key role here. It's going to take care of the broadcasts that would normally be associated with ARPs. Okay. So it's going to essentially maintain a mapping between IP addresses and pseudomac addresses. So this table here, right, 10512, corresponds to the following pseudomac address. We don't want any administrator configuration of this Fabric Manager, and we want the state here to be entirely soft, so that if the Fabric Manager happens to fail, or all the replicas of the Fabric Manager happens to fail, we can reconstruct the state, or at least fall back to broadcast. And here's how it works. Essentially, when I do an ARP, right, I want to know the MAC address for 10512, I'm going to go ask the Fabric Manager, and the Fabric Manager is going to reply back with the PMAC mapping. This mapping gets populated whenever a switch first sees a host. So whenever a host comes online, maybe it's going to do a gratuitous ARP, maybe it's going to send a packet. Basically what's going to happen is the ingress switch is going to intercept that packet and go tell the Fabric Manager of a new IP address to PMAC mapping. Okay. And the Fabric Manager is going to use this to basically populate its soft state and allow an optimization where now ARP replies only contain the PMAC address. So when this host wants to construct a packet to communicate with another host, the hardware address it's going to include is going to be a pseudomac address. The pseudomac address encodes the location of the destination host. So forwarding within my topology can proceed entirely based on PMAX. Okay, so let me spend one more minute on this. The key idea here is that within each switch, I fully know the direction that I would forward every packet based on the pseudomac. Okay, the pseudomac, again, contains the pod number and the position number. So when a switch gets a packet, it basically needs to make a determination. Is this packet determined for a host in the same pod as me or a different pod as me? If in a different pod, send the packet up. If in the same pod, right, then potentially just send it to an aggregation switch that will know how to get it to the right position within that pod. Okay. At the core, again, I know all the pods that are connected to me, and I can forward things down. So we have provably loop-free forwarding in this topology. We basically leverage up-down semantics. This was, at least to my knowledge, pioneered by a system called AutoNet out of DexCirc in the early 90s. And the constraint here is that a switch must never forward a packet along an upward-facing port when the ingress port for that packet is also upward-facing. Right? So basically this says that a packet will travel up the hierarchy and then down. It will never go up, down, up, down, up, down. to get to a destination. This says that there are some failure conditions under which there is actually a connected path between source and destination, but we're not going to be able to find it. Essentially, we're not going to be able to use it. And that for us is a valuable trade-off in getting some of the benefits that we do, namely loop-free. Okay, so for our routing protocol, there's no link state routing. Liveness is monitored by these location discovery protocol exchanges, and switches are going to convey fault information to the fabric manager. The fabric manager will inform the right subset of switches of changes in forwarding tables.
So you might take more bandwidth with our assumption, actually, because it's possible you have neighbors in your multi-level tree. You didn't need to go all the way up the hierarchy to traverse a common branch of your tree. Right. What I'm saying is, yes, you can guarantee loop freeness, but there is something you lose.
There are topologies for which actually what we lose, the biggest thing we lose is that there are topologies for which there is a path between a source and a destination that we're not going to be able to find. Right, basically where you have to, because of failures, right, there is no way for you to just on an up star, down star path get to a destination.
That's true too.
Right, and there may be other cases where you will give up, essentially you're giving up some paths. When you're giving up paths, as you point out, you're giving up bandwidth.
Which comes to the question I have, which is what happens when a switch, once configured, fails?
Right. So if a switch fails, basically the neighboring switches are going to discover the failure. They're going to notify the fabric manager. The fabric manager is going to then install forwarding states, essentially, within the affected switches. The fabric manager has a view of the topology, right, such that it can install the right forwarding state in the affected switches to forward around the failure.
That is guaranteed because it has that view that the loop freeness can be violated in that case.
Right. Right. Okay. So that's the summary of the design of PortLand. We have completed a full prototype of this running on 20 OpenFlow NetFPGA switches. We use the TCAM and SRAM and the NetFPGAs for the flow entries. We do the MAC rewriting that I described in software, and so we have the full 3-tiered fat tree with the 16N hosts implemented. We also have implementations underway for HP, Broadcom, and Fulcrum switches in our lab. I won't go through the details of the evaluation. I'll refer you to the paper there. I'll highlight a couple of things near the bottom here. One of the key scalability concerns with our existing prototype is the scalability of the fabric manager. So that's what these last two entries in the table consider. So what is the control traffic to the fabric manager? Let's assume 27,000 hosts, and let's assume somewhat aggressively that there are 100 ARPs per second from every host in your data center. That we're trying to, again, test the scalability limits here. So I think that's a large number, every host doing 100 ARPs per second. In this case, the bandwidth required at the fabric manager is going to be 400 megabits per second, which is modest. The CPU requirement is going to be more significant. So you have that same 27,000 hosts performing 100 ARPs per second based on our unoptimized, right, university quality code implementation. It would require the equivalent of 70 CPU cores to handle that load, which is substantial, but still that's a cluster of 8 or 9 machines, right, today. Yeah.
What's the assumption on the speed of call?
Assumption on the what?
Of a call.
Of a call?
Yeah, you say 70 CPU.
The cores here were a couple of generations, so 2 gigahertz Intel processors. Yeah. Now, a couple of things here. One question that we're wrestling with is, should we leverage the fabric manager to eliminate all ARPs? Or does it make sense to distribute this directory in some different manner among the switches? Or perhaps just say, you know what, go ahead and broadcast. If we have 400 megabits per second total, right, with some relatively significant assumptions of ARP bandwidth on 10 gigabit links, that's not horrible. So just let 400 megabits per second of ARP traffic through. Yeah.
But won't that impact the CPUs everywhere in the whole data center?
So you'd have to have the NICs. You'd have to have the NICs basically drop all the uninteresting ARPs. Yeah. So you wouldn't want to send those all to. You wouldn't want to have 70 CPU cores on each machine dedicated to doing the ARP processing. I agree with you. But again, this is something we're struggling with. So right now, we've tilted toward go with the Fabric Manager. But it's a little bit radical. We could say, you know what? Just dedicate some fraction, 5% of your bandwidth to dealing with ARPs under aggressive settings. Probably in practice, it'll be less than that. And don't worry about the Fabric Manager. Yeah.
How common are different type of ARPs in the data center? Because this is actually a very large assumption, right? 100 ARPs per second for 100,000 node data center.
Right. So I don't know the answer to that. If you have all-to-all communication, right? If you have everybody talking to everybody, 100 ARPs per second is not unreasonable. Right? In other words, if you've got MapReduce style computation where you've got 10,000 hosts or 20,000 hosts which are joining across 20,000 hosts, then you can certainly imagine 100 ARPs per second.
I need like ARP cache.
Right. But the ARP cache times out. That's the problem. If you have truly random communication and I have a 60-second timeout on my ARP cache, then I might run into some trouble. Yeah.
Doesn't this scale though in a cloud environment where you may have multiple VMs per host?
Right, absolutely. So now if you then multiply this by a factor of 10, okay, this moves to too big a number, right, on both sides. Yeah. If you're going to eliminate the Fabric Manager. Yeah.
My sense is that the ARP protocol itself is not that difficult to implement. You can imagine ways of changing that so that, for example, the only time you have ARP traffic and that would see if you've got in that world,
Yeah.
then I assume the ARP traffic would drop down to the noise.
So if you're willing to modify the end hosts, and perhaps you are in the data center, then I think that there are significant optimizations that you can make. Our assumption here, just from a philosophical perspective, has been the end hosts are unmodified.
No change to the host operating system.
Right. Now, I'm happy to violate, if you let me violate that assumption, I'll do it happily. But we want the network to be, again, a 100,000 port switch, and you bring whatever OS you want, et cetera, and just plug it in. Yeah.
Do you assume one VM per host?
No, I think 10 is our working assumption, but 100 is,
In your mapping, you have a pseudo MAC and a one-to-one IP.
no, the pseudo MAC, the last few bits of the pseudo MAC is the VM ID. So we would reserve, say, 8 bits or 12 bits, et cetera, for the virtual machine ID. So every IP address, every unique IP address would get its own pseudo MAC, unique pseudo MAC address. And the switch, the local switch for that virtual machine is going to do the have rewrite rules, essentially. Okay.
You mentioned you're using the commercially available switching chips.
Yes.
In the next phase.
Yes.
So how do you use them to
It's very simple. The forwarding tables. Right. We have full control over the forwarding tables, so you can basically say, look at these bits in the address, and we can say, look at the 48 bits in the MAC address, and if they match this pattern, forward them along this port. Right, so it's the exact same way that these forwarding tables work for IP today. Right, these commercial switches all have this functionality, which is nice. So again, we want to work. We will be modifying the control software, right? But you have to modify the control software. But the actual hardware we want to leave untouched. Now, we're also fortunate that some of these companies that we're working with are willing to listen for not, of course, this generation, but potentially for the next generation. If we say, hey, just give us this one little thing in the hardware, things will get this much better. But we actually have found that as far as hardware abilities, we're not placing a significant strain on the functionality that's already there.
So this would be like a layer 3 table modifier.
It's a forwarding table. Right? Basically, today's forwarding table says, look at whatever bits you want in the header. I don't care which bits. And have it match this pattern. And traditionally for layer 2, you'd have to have, layer 2 forwarding, you'd have to have an exact 48-bit match against certain bits at the front of the packet. What we're saying is you no longer need an exact 48-bit match. You just need a much smaller match, which means that the number of entries you need is very small. Okay. Whereas previously, at layer 2, you'd need lots of entries. If you were willing to go with layer 3, look at these bits a little bit further out in the packet, the number of entries would be small because I'd again have the hierarchy encoded 192/168/16 or whatever the encoding was. Okay. Yeah?
Is there any reason to decide that G5 frequencies can be taken
No, this is what we could implement on the net FPGAs. And I think that in general, going back to John's questions earlier, we would want these numbers to be much more aggressive in commercial setting. And if you care about low latency communication, the numbers here are off significantly. Yeah.
How does multipathing work?
So that's a whole separate talk that I'm not going to be able to get through. But essentially, what we do is we keep track of the bandwidth. So we're going to do per flow forwarding, and we're going to identify the so-called elephants. So we're going to assume that we can do random assignment of flows to particular paths available to us. It's not per packet. Now, interestingly, some work that we have going on right now says that the conventional wisdom that you can't do per packet forwarding is not necessarily true in the data center. Because the other very interesting effect that we're having with merchant silicon is that the amount of buffering available in these merchant silicon chips is tiny. So a few tens of microseconds, maybe, if you're lucky, of buffering. In the internet as a whole, TCP multipathing doesn't work because I might have 10 seconds of buffering, literally, on one router, right? Gigabytes of memory. So if I send a packet that way relative to that way, it could be very different arrival times. In the data center, the variation is bounded and much smaller. So one interesting question that we're asking is, should you throw out TCP? Or, if you're not willing to throw out TCP, should you throw out some of the assumptions and conventional wisdom that's been associated with TCP that's been designed for a, again, much harder deployment environment? Right? TCP, of course, we're not saying that it's wrong, it just has a much harder problem to solve than what we have in the data center. And I think there's significant wins that can be had from looking at that question. Okay, so I'm going to skip. I optimistically left some of the routing work in the talk. I'll skip large swaths of it and let's briefly discuss related work. I mentioned Seattle. What Seattle does is it has a lookup scheme, directory service using a distributed hash table distributed across the switches. Like that's something that's orthogonal to our effort, and if this turns out to be a good idea, we could have our fabric manager essentially be a DHT spread across our switches just as easily. So that's the key idea there. DCell is an alternative topology for data center networks presented by Microsoft last year. It requires fewer modifications to the switch, but basically end hosts become switches in this topology. Right? So this violates an assumption that we made that the end host should be unmodified. There's less bandwidth available on DCell as well. I already talked about Trill. This work was inspired really by interconnects for massively parallel processors, which again, in turn, were inspired by these telecommunication topologies. So lots of related work in thinking machines, SGI, etc. I won't spend time on that, but there are entire books written on this topic. And of course, similarly for HPC clusters. Recently, there's been some other work out of Microsoft called VL2 that considers similar problems to ours. Very nice work. I think the key duality between VL2 and PortLand is VL2 says, what could you do if you did modify the end hosts? Okay, basically, it's getting at exactly the point that John was making. Right? If you're willing to assume that the end hosts are modifiable, you'd wind up with a different architecture than ours. Okay? So I think it's just weighing one versus the other. Do you want to have a network-centric approach to scaling your data center or a host-centric approach to scaling your data center? Okay, so conclusions. In the data center, you have the following requirements: cost and absolute performance, packaging, energy and heat, and fault tolerance. I've shown you this fat tree as the basis for delivering on these challenges with some protocols like PortLand that allow you to manage these very large-scale data center network fabrics, say 100,000 ports plus, with significant degrees of virtualization as a single logical fabric, right, toward this goal of scale-out networking. Again, what we want to enable is modules. Right? You plug in more ports, you plug in more bandwidth, and your network scales appropriately. I'll stop here. There are a number of papers that we have and a couple of websites that you can look at for more information.
Question?
You talked about not modifying the end post. A lot of people obviously are modifying the end post in the sense of running a virtual machine monitor,
Sure.
and it incorporates a virtual switch, to use one term, and blah, blah, blah. And isn't there a fair amount one can do there without munging the operating system in the classic sense here?
So yeah, I think to me, the virtual machine monitor is the new operating system. So I think if you're willing to modify the old or the new operating system, you can do a fair amount.
Well, but I guess I was trying to distinguish. I think it's a very different proposition. Lots of people can modify the new operating system. Fewer people that are willing to modify the old one.
Yeah, so I think if you could do a lot of the rewriting, for instance, for our pseudomax in these virtual switches, right? So again, which hop do you do it at? Do you do it in the virtual switch, in the virtual machine monitor, or around the virtual machine monitor, or do you do it in the quote-unquote hardware switch that's on the first hop? I think that for us, from a design perspective, it's whatever's easiest.
Anybody else?
The other place you can do it is in a $4 dongle that you stick on the outside just before the rest of the world.
Sure. So you could have an active cable,
Yeah.
essentially.
People box.
Right.
Telling the company.
Right. So what we've done is we've introduced a new layer of indirection. And the age-old question, of course, in computer systems is, where do you insert your indirection? And you could do it in the OS, you could do it in the virtual machine monitor, you could do it in your active cable, you could do it in your first hop switch. We drew a particular boundary. One reason is that in a lot of settings, our understanding is that there are the end host system administrators and there are the network administrators, and there's sometimes a hard line between the two.
It's a hard battle between the two.
Right. So
Who do you want to help?
Right. So, well, we want it to be on one line of it. The network is responsible for getting the bits as efficiently as possible from one place to another. And that's our philosophy for the network. But I think from a design perspective, we're totally flexible with respect to whether it happens in the OS, the VMM, the cable, someplace else.
So you can even do it dynamically, subject to some rules.
Right. That would introduce some complexity issues, but sure, you could do it dynamically.
So if cloud computing is going to take over the world, and it looks like it is going to do that again, it sort of says that there are going to be two classes of machines. There are going to be the desktop client machines,
Yes.
and there are going to be servers. And you're making an assumption here, it seems, that the desktop machines are going to be the commodity, and that smart data center people will use the commodity product to build the compute power for the data center. On the other hand, you're talking about a fairly large number of machines going into each data center.
Yeah.
Order, in the case of Google, perhaps 1 million, 2 million machines. 10 years out, that could be a lot more than that even. Is that the right assumption? You think that we might have servers that migrate to the desktop as opposed to the reverse, and a similar sort of specialized networking hardware being built into machines to make them better servers?
So I think what you're asking is what's going to be the new commodity 10 years out?
I think that's really where I'm going.
And I agree with you. Our philosophy is that commodity components organized in parallel always beat out the specialized components. And they have, and this is an easy prediction to make for the future because it's happened for so long. So the point with our design is commodity components organize appropriately in parallel. If the new commodity 10 years out is different, our philosophy will be leverage that, whatever that commodity building block is, because the economies of scale is so significant. I won't predict whether it'll be 90% of the computers and networking in the world are in Google and Microsoft's data centers, so they're going to define the new commodity. That's one possible world. Or whether the heavy tail is going to outnumber them with the 100 computers that we're each going to have in our own houses for a variety of reasons.
Only 100?
Right.
You're not watching the trend.
Well, 100 of Intel class, right. Yeah.
Okay, you mentioned in your advantages and disadvantages for the layer 2 and layer 3 that seamless VM migration, the advantage with layer 2, I mean, it's a positive there.
Yes.
That's assuming that you always migrate within the same data center.
Within the same subnet, essentially, within the same layer 2 fabric.
But it's a use case like disaster recovery where you actually migrate across data centers, that's different.
Yes, so that would be, we're doing work on wide area replication as well. Multi-data center programming and multi-data center migration, et cetera, I think is a very interesting problem. But no, this work would not address that particular problem.
Question on the factory topology.
Yes.
So in a pod, in your example, you have 4 switches. Right,
Yeah, simple
edge of
example.
the aggregation.
Yes.
So what's the motivation of having the aggregation? Because if you get rid of the aggregation, you still have the same number of links down and up.
The aggregation switches are responsible for allowing all hosts within the same pod to be able to speak with one another at full speed. The aggregation switches are also the switches, so that's the key, right? If I only had one level in my pod, then there would be no way for the hosts within the same pod to be able to speak to one another. Right? And essentially they introduce another multiplicative, so the number of levels that you have in your tree determines the exponent in your scaling factor. So if you remember earlier on I said k-port switches in a 3-level factory give you k cubed over 4. That cubic comes from the fact that I have a 3-level tree. You could build a 2-level tree, but then you'd have a squared property. Right? You'd have k squared over 4 times something. I won't try to reproduce the math on the fly, but essentially, if you wanted to eliminate one level, the maximum sized cluster that you could support would go down drastically. Right? It would be on the order of k squared rather than the order of k cubed. And k squared for k equals 64 will wind up being, so it's I guess k squared over 4. It won't wind up being 1024. And 1024 ports non-blocking is good, but not at the scale that we'd like. So we really need that 3rd level in the factory.
But in your example, how do you scale to the 1 layer higher?
Again, so in the example, it's 3 levels, so which gives us the k cubed property.
Okay.
Because after that, at the core layer, right? So you're saying that if I want to scale 1 level higher, I should have
Add a 4th
another
level.
N or aggregation kind of.
You were talking about turtles all the way up, all the way down. I now know how to build a 65,000 port potentially non-blocking switch. Now I can use the 65,000 port non-blocking switch as the basis of a 2-level factory to get 65,000 squared ports. Right? So it's now you're using a small switching element to basically, if I can use 4-port switches to build 16-port switches, I can now use 16-port switches to build 64-port switches. I can use 64-port switches to build 1024-port switches. It's recursively all the way up. So now, I mean, if you want to take it to a 13-hop topology, we can support that. Right?
Well, we lost the remote people a little while ago, so thank you.
Yeah, thank you.
For more, please visit us at stanford.edu.